Welcome back to the channel. Today we're going to be talking about coax traps. These are pretty cool little devices. This one happens to be for 7 megahertz. And this one is supposed to be for 14 megahertz. And I'll talk a little bit more about that in a second. But essentially, what a coax trap is, it's a way to block RF at a certain frequency. And the method we use to do that is we wrap coax around a form, and then we wire that coax so that the RF has to travel through that coax twice. So you can see that's my input. So this is coming from the transceiver, goes in the center conductor, goes around the form, comes out the other side, and then we attach it to the shield of where we came in. So that RF has to go through the shield the same way, and then we pull that circuit out on the shield right here. So basically it goes in the center conductor all the way around the form, we loop it back to the shield, goes all the way around the form, and then the shield is our output. And because we're wiring it in that method, it's no longer a transmission line. It's a coil, an inductor, and also it has some capacitance because our two leads are right next to each other. So whenever you have capacitance and inductance in parallel, we have a tank circuit. And a tank circuit resonates at a certain frequency. So what we do is we tune this rascal to be resonant or close to the resonance of the frequency we want to block. So you can take two of these and put these in a dipole at certain spots and create a multi-band antenna by doing that. So one of the problems with dipoles that are fed in the center is that the ham bands, if you think about 10, 20, 40, 80 meters, they're even multiples. So to get from 10 to 20, we are doubling or cutting the frequency in half. To get from 20 to 40, we're cutting the frequency in half again. From 40 to 80, once again, we're cutting it in half. The problem with that is that if you're feeding an antenna from the center, it's only resonant on odd multiples. So for instance, if you had a 40 meter antenna, it may also be resonant on 15 meters, because 15 meters times 3 gets you pretty close to 40 meters. So your SWR and your resonance may be close enough. But if it isn't, then you could do something like this. So what I have outside is I have an 80 meter, 75, 80 meter antenna dipole fed in the center, close to the center anyway, and I have two of these that are in that 80 meter antenna, and they're placed so that at 20 meters it blocks the RF from going out to the full 80 meter length of that antenna. So with these in the circuit, the dipole appears to be a 20 meter antenna, which is great because instead of having to run another fan dipole off of my fan dipole, I can just put two traps in there and create a multi-band antenna out of one dipole. Now you can actually keep doing that. You can set up one antenna to have multiple traps and make it resonant on a bunch of different bands. But the problem with that is every time you put capacitance and inductance inside of a dipole or any antenna, the bandwidth will decrease. So in this case, the bandwidth on 80 meters isn't great, but I don't spend a lot of time on 80 meters, so it's not a problem for me. But the bandwidth on 20 meters is actually quite good with the traps in place. Now, the reason I took this down is because this thing has lost its resonance. It's slightly out of tune. And let's watch what the Nano VNA shows us on this right now. I'm just going to hook just a piece of coax that's been stripped, and on the end of it I've put these little connectors. Now, very important point. I've added a few inches to my antenna here. That hasn't been taken into account when I calibrated it. Now, on HF, this length isn't going to make any difference, but if this were UHF or VHF, this would not work. I would have to shorten them somehow. So at resonance, what's going to happen is the phase will change in the coil. And you can already see the phase change right there. So at 11.35 megahertz, the phase changes. So that's where this is resonant. That's a far cry from 14 meters. So that is my problem. I'm going to bring on more traces here. You can also see when I set it to resistance how our resistance goes up as it gets near the frequency where it's resonant. So at 12.925 we're down to 55 ohms. And as we get closer to 14 meters, you can see it's not very good. So this thing's low on frequency. At its resonant frequency, we're in the k ohms, 30 k ohms, etc. So this is definitely out of tune. When I built this, I wanted to order up some heat shrink tubing that was large enough to go around it. I just never did. So I figured that at some point it would go out of range, and it did exactly that. So this time around I've got some clear paint in an aerosol can. Once I get this thing back to the right frequency, I'm just going to coat it with clear enamel and let it harden up, and that should do it. Make it more permanent. Okay, now I'm down to coax and a PVC form. Let's see what happens here. When I make these, I make them just a little bit long, because that way you have the ability to change the resonant frequency just by sliding your coax together or apart. So I can actually change the frequency it's resonant at by separating the coax. I set my cursor up at just shy of 14 megahertz. And I think I'm going to have to shorten this one turn. I just can't get there. close. But no. Okay, I'm going to have to shorten it one turn. Okay, I took one turn out of this thing, which I was afraid would be too much, but in this case it worked out. So I mentioned that you don't want to tune one of these so that it is resonant right on a frequency that you might transmit on. And the reason for that is because for some reason that's beyond me, if you do that, there will be losses at that frequency. That resonant frequency will induce losses in the antenna. I don't know how that's occurring. If there are any knowledgeable hands that understand RF and understand what happens at the resonant frequency of a coax trap that creates losses, please let us know in the comments below, because I do not. I'm just going by what other hams have said. So I tune it outside, just outside of the frequencies that I'm going to be using. So in this case, we've got this thing resonant right now. So at 14,560, the resistance of this coax trap is 5 k ohms, and then as we go up in frequency, there's 580, that's 13, 14,600, 23, 14,620, 44, 14,640, 54 k ohm. So the resonance of this trap is 14.640 megahertz, which is above any frequency that I'm going to transmit on. So we're good. So before it was set up just below the frequency, I had it resonate at about 14 or 13.9 megahertz, and now we're set up just above it, so that will work. And I just took one turn out. Now the next thing I'm going to do is run this outside, and I'm going to hit it with a couple coats of clear enamel just to lock everything down. I might even put a zip tie on this to hold this together. As you can see, you can manipulate your resonant frequency by separating, spacing out that coax. It runs at higher on frequency if you do that. So anyway, let me go out and hit this with a couple coats of paint, and we'll be right back. Alright, while we're waiting for the paint to dry, let's just check this one. I was just playing around one day when I first started experimenting with coax traps, and I wanted to see if I could make one for 7 megahertz. So let's see if this one is truly resonant at 7 megahertz, just for the heck of it. Like I said, I have to wait for paint to dry anyway. One of my disappointments with the Yaesu FT891 is that Yaesu recommends that you keep the SWR below 1.5 to 1. Yeah, and I had originally built, and I'm going to do this, let's see, I'm going to just wrap that around that. I had originally built an off-center fed dipole in the hopes that I could pick up a bunch of bands with a single dipole that would work. But because of end effects, I couldn't get the SWR to be perfect everywhere. It wasn't bad, but my SWR window below 1.5 wasn't very wide at all. So I ditched the off-center fed dipole idea, and I went with this, which is basically a fan dipole. And originally it was 20 and 40 meters. And then one day I decided I wanted to add 80. So I lengthened the 40. No, I lengthened the 20, and I put 2 drops in. I'm not sure where this thing is resonant at. Oh, there it is. Okay, it's resonant below, significantly below. Looks like 3.73 megahertz is where this thing is resonant. I can raise that by separating this. There you have it. Okay, so that was low as well. But anyway, that's a coax trap. So in on the center, all the way through, run the center conductor back to the shield. You can see the shield. This comes from the center conductor at the end of this spiral, and then it goes back through the shield, and the shield becomes the output. Kind of hard to see, but there's our shield coming out. So it makes that loop twice. Inductance and capacitance tank circuit. And I'm going to go back outside and put another coat of clear enamel on my 14 megahertz trap. Okay, here's how you set this up. I can't really get rid of that glare, can I? So, fan dipole. We've got a mast, and the way that I did mine is I have a current choke in here, and then it comes out and it goes into a 1-to-1 balun. Then I have two wires coming out of this. The lower one is 40 meters. So this is our rope, and this is our antenna. So this is 40 meters. And then above that, I've got a longer one that comes out, and I've inserted my coax traps at 20 meters, and then the rest of it becomes 80 meters. So from here in is a 20 meter antenna. At 20 meters, the RF can't make it past to that coax trap. It's blocked. These coax traps present high resistance at 20 meters. But at 80 meters, it goes right through. Now, the reason I did this in the 80 meter section instead of the 40 meter section is these are also inductors. And whenever you put an inductor in an antenna, it will shorten it just a little bit. At 80 meters, that's handy, because it's a long antenna to start with. So you can imagine at 20 meters, our dipole is about 33 feet in total length. At 40 meters, it's about 66 feet in total length. And at 80 meters, we're talking about 132 feet of wire. So anytime we can shorten it, that's a good idea. Now, if you're ever building one of these low frequency or medium frequency antennas, or low HF, I guess would be the proper term, and you put it up in the air and you find that your SWR is higher than you would expect. Well, one of the bad things about most HF antenna installations is we can't really get them that high up in the air. Most guys will get them up around 30, 40, 50, 60 feet, and that's about it. So at 80 meters, well, any frequency really, you want your antenna to be half a wavelength above the ground. So at 40 meters, half a wavelength is 20 meters, or about 60 feet. Well, my antenna is not up 60 feet. My antenna is up about 28 feet. So that's a problem for two reasons. One, because the RF becomes this big bubble and the angle of radiation isn't very low. We call those cloud burners. Now at 80, it's even worse, because at 80 meters, half a wavelength at 80 meters is 40 meters, which is 120 feet. For this 80 meter antenna to radiate properly, it should be 120 feet above the ground. I'm sitting at 28 feet. That's a big problem. So, number one, it's a cloud burner. And number two, whenever you get that close to the ground on a low frequency antenna, the ground will mess with the resistance and the impedance of the antenna. In this case, it drives it lower. So the impedance is driven lower because of the proximity of the ground, and it's also driven lower because it's an inverted V dipole. Inverted V antennas always are a little bit lower in impedance. So a way that you can get around that or fix that on a inverted V dipole is just feed it slightly off center. So if your impedance is slightly low, which is causing your SWR to be slightly high, feed it slightly off center. And by that I mean you're taking this dipole, which normally has current pattern like this, and right in the middle of our current pattern is going to be our lowest impedance. But if you bring it over here, where the current is slightly less, the impedance will be slightly higher. So sometimes you can find a happy spot by slightly off feeding it off center just a little bit, where it'll be 50 ohms. Not 50 meters. So that's a little trick that I learned. You can slightly feed it off center to get it back. And I've had to do that with both this 40 meter antenna and this 80 meter antenna. Now the 20 meter doesn't care, because half a wavelength at 20 meters is 10 meters, 30 feet. We're really close to that. So my radiation pattern on 20 meters is actually quite good. But when I fed this 80 meter antenna, one leg is longer out here than the other side. So this side of the antenna is 7 feet shorter from the coax trap out than this side. And that gets my SWR down where I need it to be. Okay, I'm going to run out and see if my paint's dry. I'll be back. Okay, here's our completed trap. It's still a little bit tacky, but I'm going to go ahead and check it. And if it's acceptable, I'm going to go ahead and put it up in the air. And here we go. It looks like it's resonant at about 14.8 megahertz. Now if I come down to the frequencies where it will be in this neighborhood right here, I still got several hundred ohms, so we should be fine. Okay, I'm going to go stick it up in the air and see if it works. We'll do a SWR sweep on the antenna real quick, and if I'm really lucky I won't have to mess with the other one, but I don't think that's going to happen. I'll probably be pulling it down as well, but we'll see. Maybe I got lucky and it was just one that was out of range. Hey, thanks for watching.